Welcome to the chapter 24 video lecture. We are talking about the demise of stars. And we, in the last video lecture, talked about how our star like our sun's going to die. Now we're going to be focusing on how some of the higher mass stars die. This picture here shows a good, just quick summary. Stars like our sun expand to a giant stage, eventually planetary nebula white dwarf. We got some of the lowest mass stars, and like I said, we don't really know what's going to happen with them because they have a long lifespan. So none of them have died yet, but we figure they're going to become white dwarfs too. Then we got our supernovas. The most massive stars explode as a supernova explosion, and our focus now is what happens then. So the supernova happened. And once we kind of push aside all the debris, what do we see inside there? What do we got going on after the supernova takes place? Well, to understand that, we actually got to take a step back and talk a bit more about white dwarfs and how supernovas happen. Then we'll be able to properly understand what is left behind by a supernova explosion. So, white dwarf. White dwarfs are extremely dense degenerate stellar remnants. Extremely dense because they were crushed by gravity. The term degenerate is a very special term that's used in physics to mean a system where all of the energies are the same for objects. And for the purposes that we talk about in this class, that happens because our objects are compressed to their most highly compressed state. And when that happens, they take on a new form of matter called degenerate matter. The white dwarfs are made up either of carbon and oxygen, or possibly helium if the progenitor mass was sufficiently low. They are very dense. For a comparison here, if you have a beach ball, I worked out a little calculation. A beach ball size material would be comparable to an ocean liner, so a giant vessel at sea. So you can see in the picture here, this is a picture of a white dwarf. Now, it's not the thing that's in the center. The thing in the center is the star Sirius. In fact, the star Sirius is a binary star system. I showed you this picture a few lectures back. And the small little object down here that the arrow is pointing to is the white dwarf. So this is a system where we have an A star, and that's what Sirius is. And the other object was something that was a little bit more massive and has already died, actually. And the white dwarf is left behind here. Now, what's extraordinary about this is these objects have probably identical temperatures to them. But due to their size differences, the luminosity of this white dwarf is tiny. So, but yeah, these white dwarfs, they have an incredibly low luminosity to them because of their size. They are about the size of the Earth, but with temperatures similar to that of the sun or higher. And that actually produces this incredibly low luminosity. Now, the degenerate matter. So remember, when the fusion reactions stop in the object, gravity still exists. Gravity is trying to crush the interior of the star. Just imagine this. Look around you right now. Do you have like a piece of paper or something? Like, think about a piece of paper that you could have. And imagine taking that piece of paper and crumbling it up. I don't have any paper next to me. So just that sound is me crumbling paper up. So I'm crumbling this paper up here. And try to make it as small as you possibly can, right? You can probably compress that paper down quite a bit, right, with just your hands. But there's like a limit to that because you can only push so hard with your hands. And then maybe you can use a tool, like you can use like a hydraulic press. I see these hydraulic press, YouTube channels, and they crush paper and they can make it thin, really, really super thin. But it could still be compressed even more. So the question is, how much can you actually compress an object? Like, what's the maximum compression that an object can take? Well, when that happens, you basically have all the atoms just right on top of each other. There's no space between the atoms. Not only is there no space between the atoms, But a lot of times the atoms are ionized too, and so you can fill in a lot of space that's normally occupied by electrons. They get incredibly dense. I mean, I would imagine that if you take a normal piece of paper and you try to compress it, if you could truly compress it down to its absolute limit, it would be something that would be so small you would not be able to see it. That's how small it's going to be. And that's what degenerate matter is. And that's what a white dwarf is like. Right? Because white dwarfs are in hydrostatic equilibrium. You say, well, they don't have fusion, though. It's right. They don't have fusion. The gravity's crushing them, but obviously they're being supported by something because they still have a size to them. And what's happening here is in these objects, the electrons are actually placed back inside of the orbital levels of these atoms. They're just forced in there, actually. That's how compressed this can be, is that, like, you know, these stuff are the electrons are put back into the atoms, and then the pressure just comes from the fact that you can only pack so many atoms in a given orbital level. We call it electron degeneracy pressure. And it's just something, you probably remember this from chemistry, but remember how many electrons you can fit in an orbital level at most? 2. It's called the Pauli exclusion principle. And that's kind of that limit is a pressure, actually. It's a limitation on how compressed you can make an object. So anyway, so that's what these are like. These are highly compressed objects. So now they're related to supernovas, actually. So we have different types of supernovas. I mentioned supernovas in the last lecture, and when I talked about those supernovas, those are the type that we call type 2 supernovas. And that's when you have a really massive star like an O star and a B star, and the core collapses on that star. And when those things explode, they reach this enormous brightness, and they kind of stay bright for, like 3 months or so, and then they kind of drop off in brightness. When we look at the spectrum of these things, we see hydrogen lines, so it's clearly a star that exploded. What's happening in these type 2s is they make a white dwarf. They actually do make white dwarfs. The white dwarfs, however, are made of iron, and they're too heavy. And so as a result of that, there's too much gravity, and the immense amount of gravity can actually break the electron degeneracy pressure. It breaks them. What literally happens is the electrons are able to jump into the nucleus of the atoms where they combine with protons, and the amount of energy released in that process is enough to rip the star apart. Okay. Now, astronomers have discovered another type of supernova. We call them type 1s. And the characterization of type 1s is that they get to a peak brightness. They drop off kind of quickly to begin with. And after about maybe a couple months or so, the luminosity fades away a bit slower than it does for the type 2s. And what's really interesting about the type 1 supernovas is that when we look at the spectrum of the explosion, we do not see hydrogen in the spectrum, which initially is very odd because, most objects are made up primarily of hydrogen. So when something explodes, you would expect to see a lot of hydrogen. And if something explodes and it doesn't have hydrogen, it suggests that no hydrogen was present in the objects. Well, what could that be? That's the white dwarfs. White dwarfs don't have any hydrogen in them. So it makes sense when they explode that you don't see any hydrogen in them. There is a maximum mass to a white dwarf. And that maximum mass is called the Chandrasekhar limit. It is around 1.4 solar masses. So for the type 2 supernovas, when they develop this iron core, it's over that limit and it explodes. Now, for the type 1 supernovas, these are pre-existent white dwarfs. They've already formed. It's kind of like the Sirius system. It's already there. The white dwarfs are already present. But some mechanism gives them additional mass later in their lives. And if they get pushed above this limit, then they explode as a supernova. Okay, this limit is just enough mass to produce enough gravity to crush the atoms in the star, okay, in the white dwarfs. So how does this happen? How could you even have something like this take place? Well, this will happen in a binary star system. Now, in a binary star system, we can draw these, what we call these things called Roche surfaces. that surround the two stars in a binary system. And these Roche surfaces represent regions of space that these stars control gravitationally. So as an example, let's say I took like a planet and I placed it somewhere in this binary star system. If I place it within the Roche surface on the left, that planet will orbit the star on the left. And if I place it in the Roche surface on the right, it will orbit the star on the right. And if I place it outside of the Roche surfaces, it'll just orbit the entire system. It'll just orbit the two stars together. Now, in addition to these Roche surfaces, we have these points that exist outside of the surfaces that have significance. They're called Lagrangian points. And Lagrangian points are points of gravitational stability. So when I mentioned I could put this planet down, right, in different places here, well, it turns out that if I place a planet at any one of the 5 Lagrangian points that you see here, the planet will remain stationary in these locations. Now, the system will move, and of course, the points move with the system, but the planet will stay locked at these locations. They're gravitational points of stability. And there is an important one called L1, which exists exactly between the two stars, and it represents a boundary where the Roche surfaces touch. And you can transfer mass back and forth between this point here. That's what's happening. Here's another view of these Roche surfaces. The idea is that you could have what's called a mass transfer scenario take place in these systems. So let's just say that A is a white dwarf. Let's say B is a main sequence star that's about to expand and become a red giant. So it expands, and because of the expansion, it kind of fills its entire Roche surface with material. And it actually starts to kind of bend on one side here because it's gravitationally attracted towards A. And if it expands enough that it fills its Roche level material, that means material will reach the L1 point. And once material reaches the L1 point, then it can now fall onto star A. So B is transferred mass onto the white dwarf in this scenario, causing the white dwarf to get larger and larger and larger. And if it exceeds the Chandrasekhar limit, that can cause star A or the white dwarf at A to explode as a type 1 supernova. It actually happens in a bunch of systems. They're shown at the bottom here. You could actually have a system where you can transfer mass back and forth, back and forth, back and forth. And that kind of really dramatically changes the stellar evolution of these objects because, imagine B's trying to die here as it expands to a giant star, but it loses mass. So it can go right back in the main sequence and live longer because of this. So it's a weird scenario. But anyway, this is how a white dwarf could possibly get more mass after it's already formed. Now, how do we see these things? I mean, white dwarfs are already incredibly faint. Well, the way we usually see these things is we actually see the giant star or something that's about to expand to become a giant star. And if it's already losing mass because it's close enough to its companion, the mass actually kind of spirals onto the object. It's kind of like a funnel almost. It kind of spirals onto the object. And it forms what's called an accretion disk, and that's how the matter actually eventually falls onto the white dwarf. But that accretion disk gets insanely hot. Like it reaches temperatures of millions of Kelvin, and that will produce a lot of X-rays. According to Wien's law, temperatures in the millions are peak at X-rays. So what we do is we find these giant stars, and they have, for some reason, an enormous amount of X-rays coming from them. We're like, what's going on here? Why is there X-rays? It's because you got a scenario like this taking place. And what can happen is you have novas that can take place. Novas are just when enough mass kind of creates a little crust on the white dwarf, and then there's this temporary little fusion that takes place. And then the mass, like you have a thin fusion shell of hydrogen as like a kind of a crust on the white dwarf, and it ignites. And so the white dwarf gets bright temporarily and then goes back down. And the supernova is the last one of these when it goes over its limit. So that's how this is typically called type 1A supernovas. And these are the ones that we're going to study a lot when we talk about galaxies, because the mechanism by which these white dwarfs explode is a very precise mechanism. And it has a very predictable brightness to it. So All right. So what's made then? Okay, so we got these supernovas, right? We know these white dwarfs, they get too big. So what happens now? Well, the supernova occurs, and if the mass of the star is just a little bit above 8 solar masses, then what happens is when the electrons and protons combine together due to the immense pressure inside of this white dwarf, the atoms are destroyed and the electrons and protons can combine and create neutrons. And what gets left behind is basically a gigantic atomic nucleus that's made up almost entirely of neutrons. It's just this giant ball of neutrons. And these objects are even smaller than the white dwarfs. I mean, these things don't get more than 10 kilometers across. They're tiny things, actually. And the reason why they're so tiny is because you have removed all the electrons, and now you can't truly occupy the space that exists within an atom where normally the electrons exist. And that allows you to have densities that are absolutely ridiculous. I mean, 10 to the 14, what is that? That's huge. I mean, I did a comparison here one time. I worked out that a sugar cube, which is not incredibly big, has the weight of 100 million tons. I mean, that's enormous amount of mass and density here. So this is a very common thing that gets left behind when these supernovas take place, is a neutron star. Now, I gotta really emphasize something here. This is exotic matter. I mean, the neutron star is not made of things that you find on a periodic table. This is not normal matter. These aren't atoms here. It's just a giant ball of neutrons. Now, you may be thinking here, 10 kilometers. I mean, there are plenty of asteroids in our solar system that are larger than 10 kilometers. And those are difficult to spot, right? Got to imagine, how in the heck do we find objects like these? Well, yeah, I mean, if you look for a comparison here, white dwarfs and the Earth are very similar in size. And the neutron star, I mean, honestly, I have a little dot down there, and I'm pointing at the neutron star, but I'll be honest with you, that may be a lie. That may be a lie. I mean, that dot may be too big, honestly. Again, 10 kilometers is a rather small distance. What is that? Like 6-7 miles. It's very small. All right. So we have discovered these objects, but through a totally, well, at least a seemingly unrelated way. I'll say that. So back in the mid 60s, there was a discovery made. It was done by a radio astronomy group, and in particular, it was done by a grad student at the time. Her name was Jocelyn Bell Burnell. And she discovered in her radio astronomy work that there were objects that were discovered that appeared to blink rapidly. Now, they show a little plot here of, we see these blinks. They have little bumps in intensity here, and these little blinks they could take place sometimes once a second or even faster, actually. And this was very puzzling at first. I mean, things in space don't really move or react very quickly. In some cases, they were seeing like blinks that were taking place on the order of milliseconds. And that's incredibly fast. I mean, at the time, the only thing that was known that could do that were man-made things. So they did initially thought like, oh, maybe this is extraterrestrials, but you can't say you found extraterrestrials unless you found extraterrestrials. Like, you got to show up to the press conference with like the alien, your arm around the alien and say, hey, look, I found this alien. And that's the burden of proof you need at this point to say you found aliens. So they kind of looked into the literature. They realized that this may not necessarily be extraterrestrial in origin, but it could be a rapidly spinning neutron star. And while you normally would not see the neutron star because it's so small, if it spins sufficiently fast, it could show like these blinks that are taking place. And this makes a lot of sense because, neutron stars are very small. We're talking about these objects, the stars that produce these things were potentially millions of kilometers in size. And while a lot of the mass is released from the object through an explosion or something, a significant amount stays on the neutron star. And if you take something that is millions of kilometers across and you shrink it down to 10 kilometers across, there's a conservation of angular momentum law that says that things have got to start to spin very, very fast. So it's expected that neutron stars spin very quickly. I mean, they could spin hundreds of times per second. That's how fast these things could spin. So what exactly is going on with these things that make them blink? Well, we have a model for these neutron stars. Now, when they're seen in this manner, they're called pulsars. Okay. The objects are neutron stars, but when they're seen in this manner, we refer to them as a pulsar. So what's happening here? Well, the picture on the upper left is a depiction of what we think these neutron stars would look like if we could somehow see them up close. It would be a small sphere, like I said, about 10 kilometers across or so. And you might witness a faint glow around the object. The object, while it's mostly comprised of neutrons, would have a trace amount of some charged particles. And those charged particles would create a magnetic field due to the very fast rotation that the object has. That magnetic field would cause other charged particles to travel along magnetic field lines, and they sort of crash onto the object at very high velocities. And the places that they crash, it's like the north and south poles of this neutron star, the places where they crash would be like two really hot spots on the neutron star. And they would effectively produce beams of light because they are so incredibly bright, right? So we have this idea that they are similar to lighthouses. The way a lighthouse works is you have, a light source and something that rotates, either lenses or mirrors of some kind, and they produce these beams of light that spin. And if you're out in the ocean, you just see these occasional blinks every time one of the beams of light points at your ship. Well, just like that for the neutron star. Now, the neutron star could actually spin in a much more complicated fashion, but what's still the same is that a beam, as it spins, will point towards the Earth and produce a blink. And then it moves out of our field of view, and then the other beam can come and point at us, and we see another blink. And so in that way, they are very similar to lighthouses. And that's how we're able to discover these objects, is because normally the neutron stars, they're so tiny that they don't produce enough luminosity for us to really see what they look like. But since they can spin and produce these beams of light, then we end up seeing them as pulsars. So that's true. In fact, I have a question for you. I haven't had a lot of questions recently, but I have a question for you. This picture is showing a neutron star. They're showing how it rotates, and the black lines that are coming out of it are the say the beams of light. And at this moment, if there is an observer at location A, they're currently seeing a blink because there's a beam pointing at them, right? So imagine how this object would spin. And do you know if any of these other letters would not see a blink from this object? So think about this for a minute. So the answer here is B. B would not see a blink as this thing spins. You can see a little animation here. I have my expert PowerPoint animation skills. So A sees a blink, C sees a blink, A sees a blink as this thing spins, but B just never happens to see a blink. And that's certainly possible. The neutron star can rotate in such a way that a beam doesn't actually point towards a particular observer. So a neutron star might be there, and A and C sees a pulsar, and then they know, there must be a neutron star there, but B sees nothing at all. So we have the statement that we can make at the bottom here. And the statement is that all pulsars are neutron stars, but not all neutron stars are necessarily seen as pulsars. So we almost never see the neutron star by itself. We see pulsars. And that means we only know of some of the neutron stars that exist. The other neutron stars just don't point at us, so we don't see them. Okay, so the obvious question now, the obvious thing to do is, okay, what makes neutron stars? Supernovas make neutron stars. So it makes sense. We should look at the centers of supernova remnants, and we ought to find a bunch of pulsars. So here's the Crab Nebula. The picture on the right is an X-ray image, looking a little closer at the center of it. And sure enough, this object right here, okay, right at the center of this thing, it's blinking. It's a pulsar. We did find a pulsar at the center of the Crab Nebula. So that provides us some pretty good support for the idea that these things are connected to each other. Here are the pictures, actually. These are really rapid images. These images are separated by just a few milliseconds. So there's pictures at the top here, visual wavelength pictures here. Down here we have X-ray pictures. It's really important that you see the blink in two different wavelengths like this. We call these things counterparts. And it's important that you see counterparts. So it blinks in visible light and blinks in X-rays as well. And that's good because it means the source of the light is some kind of thermal radiation. It is due to these hot spots that exist on the neutron stars. So, and you can see these blinks, they're like, I don't know, they look like they're about 15 milliseconds apart. Now, 15 milliseconds, what is that? I mean, if you take the time in milliseconds and take the inverse of it, that would tell you how rapidly this stuff rotates. So, trying to do that here. Yeah, it's about a little over 60 times a second. So this particular object here, if it really is showing pulses as frequently, it's rotating, like about 60 times a second here. This is incredibly fast. And just imagine this, right? You have an object that's several miles across and it's rotating like tens of times a second, or in some cases it could be 100 times a second. That's totally extraordinary to see something like that. And so we do look at a lot of supernova remnants, and we do find a lot of pulsars there. Not every supernova remnant has a pulsar in it. Not every one. We know one reason why, right? It's possible that it doesn't rotate in such a way that we can see. We can see the pulsar. So some other things could form there, and one of the things that can form there are black holes. So this is also a product potentially of a supernova explosion. All right, so black holes are kind of an extension of studying neutron stars. Neutron stars, just like white dwarfs, have a limit to them, right? The Chandrasekhar limit, white dwarfs, is 1.4 solar masses. The limit, it's not called the Chandrasekhar limit, but the limit for neutron stars is 3 solar masses. Neutron stars are supported by what's called neutron degeneracy pressure, and we know that there is a limit to that pressure. If you pack on more than 3 solar masses of material, then that pressure breaks and something happens. We don't know what that something happens is. We know of a consequence to that something happening, and that consequence is the creation of a black hole. So there's kind of a couple different issues that we need to think about here. Once you break the neutron degeneracy pressure, the object continues to shrink in size. We do not know of a mechanism beyond neutron degeneracy pressure that could support an object against gravity. We know neutrons are made of things called quarks, and maybe somehow quarks get into some kind of configuration where they can support things against gravity. We don't know. And if there's nothing that can support an object against gravity when the gravity is that extreme, then gravity basically crushes everything down to a single point in space, which we call a singularity. And that's a very strange and somewhat uncomfortable idea. I mean, points don't truly exist in three-dimensional space. I mean, anytime you have a point, you can usually measure it and say it actually has a size to it or something. But we don't know. And the reason we don't know is because the result of the neutron star break-in is to create a black hole. But to understand why a black hole is created, we have to talk about a seemingly totally different subject, and that subject is called escape velocity. So the idea of escape velocity is the following here. When you want to say, launch something into space, you have to overcome the gravitational forces that are at work. Now, the way we do that currently is we have rockets, and they have thrust, and there's a constant force that pushes them up and out of the atmosphere. But the idea of escape velocity is not necessarily about thrust. It's more, how fast can I throw something into the air and it would be able to escape the gravity of the Earth? Just imagine you have a ball in your hand, right? You toss it up. What happens? It goes up to a certain height, and it slows down during that, and it stops at some point, it falls back down, right? Well, you could throw that ball up faster, and it would go higher, but at some point it would slow down, stop, and fall back down. So the question you can ask yourself is there some kind of speed that I can throw this object up? And it may slow down because of gravity, but it doesn't actually ever stop and fall back down. And that particular topic, that particular concept is called escape velocity. Now, this assumes that there's no resistance from the air. Obviously, air resistance is another factor, and we'll just don't worry about air resistance for this initial argument here. Well, yeah, the Earth has escape velocity. Assuming the atmosphere is not interfering with the object that we throw, we'd have to throw the object up at about 11.6 kilometers per second, which is really fast, like 8 miles or something per second. It's incredibly fast. And if we did that, the object would slow down, but it won't come back down. Okay. And this is all due to gravity, so you can play around with different factors. Like I can launch something off of a mountaintop, and that wouldn't need quite as much speed. If I were to, imagine the Earth was smaller but had the same mass, that's stronger gravity, and I would actually need a higher speed to do that. So there's different values that you can come up with here. Well, some person, his name was Karl Schwarzschild, had an idea. We recognize that there is a speed limit in physics. You can only go so fast, and that speed limit is the speed of light. And so there's a question you can ask yourself. Could you construct an object that is so dense that the escape velocity would be equal to or greater than the speed of light? And that's what Karl Schwarzschild thought about. And he came up with a recipe. And the recipe is called the Schwarzschild radius. It's an equation. You can see the equation right here. It involves the number 2, the gravitational constant g, the speed of light squared, and m, which is the mass of the object. And this is a recipe. For that given mass, if you somehow could compress that mass down to an object that's smaller than the Schwarzschild radius, then you have made an object with an escape velocity that is unattainable. You create an object with escape velocity greater than the speed of light. So you can't launch things off of this object. Not even light can be launched off of this object. In fact, what it would create an inescapable object. You could do nothing to leave this object because gravity is too strong to allow it. And that's what the Schwarzschild radius is. Here are some examples for objects in different Schwarzschild radii. You see the sun's on here. It has a mass of 1 solar mass. And if you put that through the equation, you get out a distance of 3 kilometers. Our sun is not currently a black hole. Why? Because it has a lot of its mass outside of 3 kilometers. However, if you somehow were to compress all of the mass of the sun to a sphere that is 3 kilometers or less, then the sun would become a black hole, actually. You see on here star with 3 solar masses. Now, the 3 solar masses is the upper limit on what you could have for a neutron star. The Schwarzschild radius for a 3 solar mass object is 9 kilometers. Now, you might remember from when I first introduced to you neutron stars that their typical size is 10 kilometers. So neutron stars are just barely larger than their Schwarzschild radius. And if anything would cause them to shrink further, they would become a black hole. So that's the connection we're making here with this original statement we made. We don't know of a mechanism to halt the collapse of a compact object with greater than 3 solar masses because in the process of that happening, a black hole is created. So no information can get out. No light can get out. We can't see inside of there. There may be a mechanism. There may be something like a quark star. Like I mentioned, the quarks could somehow do something. Or maybe some new physics happens inside of it. We don't know. We'll never know. It could be a singularity too. It could be this uncomfortable notion that we actually have points in space. But we will never know because a black hole is made in the process. And that's how this happens. Gravity can be so relentless. Gravity can crush objects so greatly to create these situations. Now, you notice Earth is on here. Earth has 3/millionths of a solar mass, and its Schwarzschild radius is an adorable 0.9 centimeters, basically a centimeter. So that means you could take the entire Earth, right, all of the people and rocks and cars and mountains and trees and everything, and if you could somehow compress it into what effectively is the size of a pencil eraser, you make yourself a little mini black hole that's made up of all of the mass of the Earth, right? So just to give you a sense of how insanely dense this object has to be, right? The entire Earth is put into the pencil, the eraser of a pencil, right? But gravity can do this and does do this. So what I'm going to describe to you are the things that we definitively know about black holes. You might have heard a lot of bizarre things about black holes. The idea of wormholes and the idea of white holes potentially. The idea that you could travel through a black hole and end up somewhere else in the universe. I mean, these are all speculative things. And I will explain a little bit later in the lecture here, why those things exist. But I want to first start off with the solid science. The picture that you see here is what we believe to be the anatomy of the black hole. Now, I'm going to go with the singularity belief. There could be something else going on inside of the black hole. Don't know. We don't know. I'm going to go with singularity. The vast majority of physicists kind of go with the singularity idea. So all of the mass is somehow shoved into this infinitesimally small point called the singularity, and that lies at the center of the black hole. At a distance from the singularity outward, defined by the Schwarzschild radius, is what would be the extent of the black hole. And when you reach the end of the Schwarzschild radius, you reach a region that we call the event horizon. And so let's say that's 9 kilometers, right? Because that's what it is to the neutron star. So all of the mass is shoved into the singularity, and for 9 kilometers on every single side of the singularity, there's simply nothing. It's a void, it's emptiness. If anything were to exist there, it would just be shoved into the singularity. And then 9 kilometers out is the event horizon. What's at the event horizon? Well, nothing's at the event horizon. It's a mathematical boundary, but it's considered to be kind of the point of no return. You cross the event horizon, you're not getting out. Now you're going to be part of the black hole because there's no means to escape the black hole once you've crossed that boundary. There's nothing actually at the boundary, though. The event horizon sort of represents for us the extent of the void that is the black hole. It's like a region of space that is cut off from the entire universe. You can enter, you cannot exit. And in fact, the term event horizon is a really great term. If you were to throw an object into a black hole, you would watch it travel closer and closer and closer. Once it crosses the event horizon, you will no longer see it. So it is quite literally the horizon of events, which is a really great name to call it. But that's as much as we can say about the anatomy of this black hole. It's just a region of space that is cut off due to the intense gravity. Now, what happens when things become the black hole or part of the black hole? So if the matter forms a black hole or enters the black hole, well, it basically loses all of its properties. So if I threw a teddy bear into a black hole, what would be retained? Well, the teddy bear has mass. It might have some kind of spin associated with it as it falls, and so it has some kind of motion, and that would be part of the black hole. And then if it has any electrical charge, it would have to be preserved. Now, why these three things? Well, these are fundamental laws of physics: conservation of mass, conservation of charge, conservation of angular momentum. We don't think, even in the situation of black holes, that you would violate any of those things. But the teddy bear, as it gets thrown, will be completely shredded in a process that we call spaghettification. Yes, that is actually the name of this thing. It's called spaghettification. And what's happening here is, and they're showing this astronaut going feet first into this black hole here. The idea is it's about tidal forces. You remember tidal forces when we talked about the moon. Let's talk about the astronaut here. Say the astronaut is 6 feet tall. If you're jumping into the black hole feet first, your feet are 6 feet closer to the black hole than the top of your head. Your feet feel a stronger gravitational pull than the top of your head. And there are tidal forces that happen to you. And those tidal forces act to stretch you out. Your feet are falling faster into the black hole than your head is. And it causes your body to be stretched. And this would be so extreme that it would basically stretch you into this strand of yourself. So thus the term spaghettification. It kind of stretches you into spaghetti strands, so to speak. It's a little gruesome. But in the process of doing that, the atoms are likely destroyed. Any structure that the atoms had is destroyed, and the only things preserved would be, you would be adding mass to the black hole, which would slightly increase its size. And of course, charge and angular momentum would be stored in there as well. We do know black holes can spin. We've seen profiles of voids of space that show the aspects of spinning. So we do know that that can occur. Obviously, we'll never know about charge because it requires information to get out. We can't get information out. So this is a computer-generated image of what a black hole would look like if you are dangerously close to the black hole, I guess you would say. This is how the appearance of it would look. And now you'd have to be incredibly close to this. If this is a black hole that was formed by, say, a neutron star, you would be too close for comfort. Let's just say that. If you're in a spaceship, you're probably not going to get away from this thing. But anyway, if there's nothing between you and the black hole, you would just see emptiness in front of you, right? And the edge of that emptiness is the event horizon, right? There is a ring that forms around the black hole. It's called an Einstein ring. And this is caused by the fact that the black hole is so dense that it alters the space-time around it. It bends space-time in such a way that light will travel in directions along the bent space-time. In fact, the Einstein ring represents light that actually exists behind the black hole that's being sort of bent around it, much like a lens, actually. In fact, black holes and other really dense forms of matter do create an effect called gravitational lensing, and that's something we'll talk about when we get into the topic of galaxies. But gravity can act like a lens and change the direction of light. And that's what the Einstein ring is. It's a version of that kind of bending. You'll notice that inside the Einstein ring, from the ring to the event horizon of the black hole, is a mirror image of what exists outside of the ring. So this black hole is mirroring the space around it. You'll notice over here that this dark portion of the Milky Way galaxy is the portion that's over here. There's like a little light source right up there that's also down here. This object here is located here. So this Einstein ring is inverting the light that comes from outside of it. And then outside of that ring is a lot of distortion that occurs. And sometimes the distortion is really obvious. And as you get farther away, it still exists. It's just not as clear. Sometimes we detect this minor distortion of light that's near a black hole, and it's called microlensing. But this is pretty much what we expect the black hole to look like. Now, we have imaged a black hole once. And this was done, now this is being recorded in 2023, so I think this was done almost 5 years ago now. It was a series of telescopes that got together and through an interferometry technique attempted to image the supermassive black hole that lies at the center of the galaxy M87. This black hole, now when we use the term supermassive, we're referring to black holes that have a mass much larger than that of a star. So we're talking about millions or billions of solar masses. The black hole at the center of our galaxy, which I'll talk about when we get into our galaxy, is millions of solar masses. This one's billions of solar masses. And these are a bit of a mystery. It is not entirely clear to us how billions of stars could form into a black hole. There is probably another mechanism that causes this to take place, and that mechanism is unknown to us at the moment, at least at the time of this recording. So I hope you're in the future and listen from the future, and we figure this out. And if we did, well, you're fortunate to be in the future to learn what this is. I would like to be in the future and learn what this is. It's a big mystery. It's pretty wild stuff. So anyway, this black hole is obviously enormous. Its Schwarzschild radius is 120 AU. That's larger than our solar system proper. The accretion disk is 25,000 AU. It has enormous accretion disk. There is material actively fallen into the black hole. It eats 90 Earths a year. So this is the picture here. It's not horribly, it's not terribly focused, but it's the best we can do. This thing is very distant. It is in a different galaxy after all, and it is difficult to image this, but this is the picture that we got. So we see the accretion disk around it, and we see the shadow inside, indicating the presence of that dark black hole that's there. It's pretty neat that we got this, and we'll probably image more of these in the future as our technology gets better and it becomes easier to do. So how do we find these things? I mean, obviously we took a picture of one. Here we saw this, right? But how do we normally find this stuff? Well, usually you find them because they're part of compact binary systems. So we kind of talked about that, it was earlier in this lecture, with the white dwarfs. Black holes and neutron stars can be part of binary systems too, and they can also pull matter off of a companion, and they produce tons of X-rays in the process. So it's an X-ray binary. But the idea with this X-ray binary is we can attempt to work out the masses of the objects. So say we have this system right here where you have this O star. Maybe you know the O star is, 20 solar masses of material. And you know it has a companion because there's a ton of X-rays flying out of it. There's motion that indicates it's part of a binary system. And say you have all the components that you need to work out the details of the binary star system, and you work out that the sum of the masses in the binary system is 60 solar masses. Well, you can see 20 of it, but you can't see the other 40. If you can't see the source of light, it's not obvious to you where it's coming from, and it's not the result of a resolution issue. It has to be a black hole. Right? If it's over 3 solar masses, then it's an unseen companion. There's no other thing that we can see here. Basically, this technique is how we discovered the black hole at the center of our galaxy. We noticed there was a ton of stars orbiting some unseen companion, and when we work out Kepler's laws, we got millions of solar masses of material. So this is how the first black hole was discovered. It's called Cygnus X1. It was discovered as part of a binary system. Most black holes are discovered in this way. They're just unseen companions, so we detect the presence of a large mass there. Some are detected through microlensing. We obviously imaged one here. But usually when we have something that's producing a ton of energy and there's a source that's unseen, it's usually the result of that. And when we can work out masses, we get that. So the final thing we want to think about here for black holes is how exactly are they going to be created? I mean, we know that you could take a neutron star And you could pack more mass onto it, so there's clearly like a mass transfer scenario in a binary system that could do it, just like the type 1a supernovas. That certainly could happen. But the way we envision most of these things happening is through the death of a very massive star. You're talking about stars that are 25 solar masses or greater. You're well into the O-type stars. And what's interesting about these things is when an O-star like this dies, you sort of expect a supernova to take place. Well, something different happens, and we call that a hypernova. And instead of the star exploding, what happens is the core collapses, and because there is so much mass that collapses into the core, a black hole is immediately created instead of a neutron star. And instead of an explosion, you have an implosion. And the star is just immediately swallowed up by the black hole. There is sort of several frames of an animation being shown here on the right-hand side as to a process like this. So the black hole is instantly made, and the black hole just starts to swallow up this star. And the process of doing that produces these enormous jets of energy. They're called gamma ray bursts. And the gamma rays themselves are short-lived. They last just like a few seconds. It's a burst. And then there's this sort of residual glow that lasts for maybe a couple days as the rest of the matter is slowly gobbled up by this black hole. But this is the way we're able to see how some really massive stars die and black holes being made in the process here. Now, gamma ray bursts can happen from other things. The collisions of neutron stars can cause a gamma ray burst, or a black hole and a neutron star collide. That can create a gamma ray burst. But hypernovas are another source of these things. All right, so what I described to you here is, for the most part, like the definitive science behind the black holes, which you could see there is not an incredibly large amount of. I mean, this is not going to end our discussion of black holes by any means. They play a very important role when we study galaxies, so you'll hear a lot more about them there. But in terms of what a black hole is and what it does, that's sort of it. That's what the definitive science is known about it. And so I mentioned a little bit earlier that there's a lot of other aspects that you hear about for black holes. And what's that about? What's this idea of a wormhole being created? What's this idea of maybe jumping into a black hole and being teleported to a different part of the universe or something like that's being created? Well, this is the difference between, in science, what we call speculation versus reality. And let me give you an example of this. So one of the first things that you learn when you take physics is a subject called kinematics. And kinematics is just a series of equations that explain, how an object travels given an acceleration, say, initial speed. So, like, if I take a baseball and I throw it, overhand, just kind of toss in some random direction, as long as I knew, how fast did I initially throw it? What launch angle did it have? How high off the ground was it when I threw it? If I know those initial details, then the equations of kinematics will be able to tell me how far it flew, how high it went, how long it was in the air, and all that stuff, right? But here's something interesting about these equations. Depending on which equations you use and how you solve them, you can get additional answers. In fact, if I talk about throwing a ball, like a baseball, across a certain distance, the equations that I use to solve this will give me a second result. And the second result is that the ball lands behind me before I throw it, which is nonsense, right? No way the ball lands behind me before I throw the ball. But the reason why it does that is because it uses mathematics, and it uses a parabola to model the trajectory of the ball. And the parabola has two answers. There's one in front of me and one behind me. Now, I know the one behind me is nonsense, and I reject it. It's just the math. Math's a tool, and the tools can do a lot of unintended things. But something interesting happened in the 20th century where math got very sophisticated, and when we were using it to solve some of our problems, we get these seemingly nonsense results. And then somebody really clever says, is that really nonsense? And they do experiments and discover, no, this is actually makes sense. I mean, the whole ideas of quantum teleportation, quantum tunneling. In fact, some of the most highest powered telescopes is based on this idea of quantum tunneling, where matter can actually just teleport through substances. That sounds like nonsense, sounds like science fiction, but it's true. It was a prediction of quantum mechanics, and it turns out to be true, and we actually are using it. Electron scanning microscopes use this technique. It's called electron tunneling or quantum tunneling. This can happen. And so some of the most important discoveries that took place in physics is looking at what the math says and trying to figure out, is this nonsense or is this real? So when you hear these crazy things about black holes, like wormholes and traveling to different places in the universe by going into a black hole, the math tells us maybe. But we don't know if it's extraneous solutions because the math is just doing things it wasn't intended to do, or if there's truth behind it. And so that some of the frontier stuff that's happening in physics, a lot of it is experimental. Some of it's philosophical, actually, because you have to really start thinking about what is really reality versus what's speculation. And sometimes things that seem like they're foolish, well, you just got to test them out and see if they really are foolish or not. And that's what a lot of the stuff you hear about black holes comes from, is the math says it's okay, but we don't know if it truly is okay. All right, anyway, that takes us to the end of chapter 24 here. It takes us to the end of our discussion of stars in general. And starting next week, we get into galaxies. All right.